Okay, so yesterday we started talking about the law of cosines. Now, you want to go ahead and use this given certain situations. Basically, if you don't have a pair, an angle measure and a side length directly across from it. If you have that, you can immediately go with the law of sines. The law of cosines works great. You just have to be careful. Once you use the law of cosines, typically you can go ahead and go back to the law of sines. What do you just have to be careful of? What am I referring to? Well, not the ambiguous case. Okay, what's that, Evan? There you go, supplementary angle. So we're talking about if you go back to the law of sines, and let's say you take the sine inverse to find an angle measure, but that angle measure turns out to be obtuse. Sine inverse will only give you the supplement angle to what the actual angle is. So you'll want to make sure that you know the angle you're about to find is not obtuse or acute, or you can just go ahead and stick with the law of cosines. Okay, I always typically just tell people stick with the law of cosines. It's really not that much worse. The calculator is really doing a lot of the heavy lifting. Eli?
So the law of cosines work in every case the law of sines would work.
Well, let's take a look at some of those problems. Off the top of my head, let's see. Okay, like in this one here, let me go ahead and just set up the triangle. So if I have triangle A, B, C, so A is 50, this is 30, and this is 9. Could I start by using the law of cosines? No. No. Because at the very least, I either need 2 of the side lengths and an angle measure, or I need all 3 side lengths. Yeah, so in this case, it's probably best to go with the law of sines. Okay, so they're not just interchangeable with one another, if that's the question you were asking. Okay. All right. So let's get back over here. Let's talk about the pattern very quickly. I think we were on this slide. Okay. And the last thing we did yesterday was I was showing you just an oblique triangle, a triangle that doesn't have a right angle. No matter what the name is, the pattern you always see for the law of cosines is going to remain the same. We were looking at ABC yesterday. I think we ended up with MNO. Is that right? Okay, let's do another one. Let's say X, Y, Z. Okay, so this would be side Y, side X, side Z. Okay, the little lowercase letters are going to be the side lengths. Of course, the uppercase are the angle measures. So let's say I started this with side Y. We always square that side, but what do I do for the rest of the formula? What's the pattern? Okay, there you go. So I take the other 2 sides, I square them, and then I add them up. Then I subtract 2 times the product of those times the cosine of y. So if I started the equation with side y, I'm going to end with angle y. The same thing if I started with side z, I would end with angle z. Does anybody want me to write out one of the other ones? Okay. So the thing I really just want to emphasize here, I mean, this is going to be provided to you on your formula book, but the pattern remains the same for every name you could possibly give a triangle using the 3 vertices. Okay, well, let's start looking at some problems here. Solve the triangle. So this is going to be ABC. Let's see what I have here. So here's A, B, C. All right, we know side A is 12, side B is 17, and side C is 23. Whoops. Okay, and this solved the triangle, so all I need to do is go ahead and find the remaining sides. All right, so which angle do you want to go ahead and start with? That depends on what formula I'm going to write. Do we want A, B, or C? You just want to start with A? Let's do it. Okay. So if I'm going to start with A, my equation would have to begin with what? Oh.
A squared.
Now, if I want to start it with B, that's fine. Okay. So 12 squared equals. So I'm going to take the other 2 sides, square them. Okay. Then I'm going to add them. Minus 2 times 23 times 17 times the cosine of angle A. So I started with side A, so I'm going to end with angle A. All right. And we can just go ahead and rewrite this. We talked yesterday, if you want to go ahead and immediately plug in, that's fine. I've always preferred to write out the equation and then just kind of rewrite it based on that. So I know that cosine of A would equal up top 12 squared minus 23 squared minus 17 squared, and then I'm going to divide by that coefficient product. Negative 2 times 23 times 17. Okay. Did anybody want me to go through manipulating the equation, show you how I got that? No? Now, we're going to go ahead and figure out a decimal value for this ratio, but then I'm going to ultimately have to do what? Inverse cosine. There we go. Okay, so let's see what we got here. I'm going to go ahead and just plug it all together. So let's see here. Let's get rid of that, document B. So I'm just going to go ahead and type everything into cosine inverse, control divide. So let's see. So we had 12 squared minus 23 squared minus 17 squared all over negative 2 times 23 times 17. All right. So we won't know what the actual ratio is, and it doesn't matter. So what should I get when I push enter? Okay. So about 30.5. Hey. Okay. All right. So let's say about 30.5. The angle measures, we'll go ahead and write them to the nearest tenth. Okay. So A is about 30.5. Okay. Now here's the thing. In this triangle, if there is an obtuse angle, it would have to be what? Now why is C different? There you go. It's across from 23. So now no matter what happens, we can feel pretty safe in saying that angle B would have to be what? It would have to be acute. Okay. Because remember, in these triangles, you're either going to have 3 acute or you're going to have 2 acute and the 1 obtuse. Okay, so the only one we have to be careful of is that angle C. So if I wanted to, I could use law of sines now that I have a pair to go ahead and find angle B. Because I know that one's acute, we shouldn't have a problem with it. Or we could go ahead and continue with the law of cosines, go ahead and find another angle, maybe even find angle C. What would you guys prefer? Let's actually go for C. Okay, let's go for C. Now, if I'm going to go for C, I have to use what? Law of cosines, because cosine inverse is not going to give us that problem. Only sine inverse if it's going to be obtuse. So if I want to go ahead and find angle C, what's going to start my equation? So 23 squared equals 12 squared plus 17 squared times what? Times cosine of angle C. Okay. And now I'm just going to solve the equation for cosine of C. So I'm going to subtract the individual terms, divide through. So I'm looking cosine of C is equal to, up top, 23 squared minus 12 squared minus 17 squared, all over the product coefficient, negative 2 times 12 times 17. And then I can just put the whole thing in while I take the inverse. All right. Okay, so let's come back over here. Cosine inverse, control divide. So what was it? 23 squared minus 12 squared minus 17 squared all over negative 2 times 12 times 17. Okay, what should I get when I push enter? Okay. So had I used the law of sines to find angle C, would there have been a problem? Yes. Okay. There we go. So it actually would have given me the difference between this and 180. It's only going to give you the supplement. So 103.6. And again, the thing about these, I always draw the triangle the same way. And ultimately, that really doesn't change anything. The diagram may not be accurate, but all your information will be. Okay. And then, if we really wanted to get the practice, we could go ahead and use a law one more time. But since we have 2, we could just do what? Just add and subtract from 180. There we go. Okay, so I'm going to take 180 minus, here's the first angle we got, minus the second angle. Okay, so I'm getting angle B, looks like about 45.9. Okay, all right, 45.9 degrees. There you go. You know, he has to be careful. He really shouldn't drink and derive because then he's going to be a rectangle. Rectangle. That's super awesome. What? Super out there. Is that still good or bad? She's just shaking her head. I don't know. Okay. All right. But there you go. I'll let y'all be the judge. Your silence obviously says what it is. Okay. All right. So how are we feeling about the law of cosines? Not bad. Okay. A little more practice, I think we'll be, doing okay. Let's try another example. See what's going on. I thought that was pretty clever. Don't drink and derive. You know? How many people are going to try to do calculus or math studies while they're driving?
I like Mr. Heinrich does that.
That would be cool. I'd like to see that. And I'll bet he does it very well, too, if he were to. Because he makes me feel stupid. That guy's like way up here, and I'm like way down here. Feel free to disagree at any time. I mean, that's okay.
Well, it's all relative.
Wow,
There's
there's
a difference between you and Mr. Heinrich that I'm like on the first floor.
Oh, come on. How many times have I stood up here and made a mistake? I'm remembering very well the time zones. Okay. Not forgetting the time zones. Okay. All right, well, moving on. Okay, a road goes up a hill for 895 feet, then flattens out by 8 degrees and continues up the hill for another 542 feet. Engineers want to build a road that climbs the hill at a constant slope. What would be the length of the new road? Okay, do we feel ready to try one on our own? You want me to give you maybe a couple of minutes to try and get the problem set up? Okay, some people are saying no. Do I need to help you get the diagram going? Okay, so let's see what we have here. Okay, a road's going uphill for 895 feet. So let's just go ahead and draw this right here. Let's say it's 895. Now it says then it's going to start to flatten out by 8 degrees. So what does that mean? Like, how am I going to draw that? That's exactly right. So imagine if that road kept going, then it's going to tilt, as he said, 8 degrees. Okay. And you continue up on this path for another 542 feet. Okay. And we want to go ahead and build it at a constant slope, so that would be just connecting these 2 points right here. So what's the length of the new road? Oh, that's what we're trying to find out. Okay. Where's my timer? There we go. Let's start with 2 minutes and we'll see. Yeah, when I get problems wrong like that, I'm just always thinking it's my asphalt. I was trying to think of a road joke, asphalt, fault. I was trying to rely on the second part of that, not the first part. Okay, so just making sure everybody was on board with that. Okay. Oh, Lord. All right, that's 2 minutes, and you may or may not be done, and that's okay. But let's take a look. Now here, we don't actually have to solve the entire triangle. We're only looking for the length of this third side right here. Well, what else do we know in the diagram?
The angle of, I guess, the little big X of angle
Because I'm hearing something. I could have sworn I heard something. Okay. But what was that, Eli? I'm sorry.
The angle measure of, like, I guess, we call it angle X, kind of.
You talking about the angle directly opposite x?
Yeah.
Okay, there we go. Yeah, so imagine this is a straight line. I mean, my diagram isn't 100% accurate, but we know that the measure of this should be 172 degrees, right? Because a straight angle is 180. All right. So how would I write my equation using the law of cosines? It would start x squared, okay, equals 895 squared plus 542 squared. Ooh, just enough room. Almost ran out of room there. Okay, that's exactly right. Now remember, we're looking for x instead of x squared, so I'm just going to take the square root of that entire expression, and let's see what we end up with. Hopefully we all get the same length of road. Let's see here. So I'm going to get rid of all of this. So control square root. So let's see here. We had 895 squared plus, what was it, 542? 42 squared minus 2 times 895 times 542. And then we want the cosine of 172 degrees. Okay. So what should I get when I push enter? Okay. 1,433.7. Do they give me a length here? Feet. There we go. All right. So 1433.7. You can even make the argument for 1434. Okay. I'll go ahead and put the 0.7. 1433.7. There we go. Questions? Okay, how many people got that one right? Okay, so there's not a lot of hands going up. Is there anything I can do to help out? I'm sorry, what? Oh, just hadn't finished yet? Okay. Well, we were on the right track. There we go. Okay. All right. You know what? And looking at this triangle, I mean, I know that obtuse triangles are always sad because they're never right. Because they're never right. Dang it. Oh, yeah. Okay. All right, so different concept. Now we're going to start looking at finding the area of oblique triangles. Remember that the area of a right triangle could be found by using 1/2 base times height. You've been using that for many, many years, way back in your academic careers. Okay, but what we're going to go ahead and start to look at is if you have an oblique triangle, if you know the angle between two sides, basically the included angle between two sides of a triangle, then you can go ahead and use this formula right here. 1/2 the product of those two sides times the sine of C. That's going to be the area. Okay, so that right here, if this is like A, B, and C, then you'd be using these two sides and this angle. So there are two other vertices that we can go ahead and use, and it's basically the same formula, but you're just writing it differently for the other two vertices. Like for example, what if the included angle I had was A? Well, then what would the other two sides be? If I had angle A as the included angle, it'd be 1/2 what? BC, and then times the sine of angle A. Okay. Or conversely, if I had angle B, well, what two sides would B be included between? Okay, so that'd be 1/2 AC times the sine of B. Okay. All right. So you don't need to worry about, knowing the base and the height anymore. I mean, we could actually probably go ahead and find it. You could always drop yourself an altitude here, but this is just another way to do it. So find the area of the non-right triangle shown in the diagram. So we have all three sides, but in order to find the area, I am going to need an angle measure. And it doesn't matter which one. So let's go ahead and I'll just leave this as A, B, and C. So we are going to have to start the problem using the law of cosines to find that angle measure, and then I can use that with the formula to go ahead and figure out what the area is. So, Emily, what do you think? A, B, or C? C. Okay, so let's go ahead and say this is my included angle, and these are going to be the two sides. Okay, so first, what would the equation be to find angle C? Okay, so 5 squared equals. There we go. Okay, and just like we've done several times before, I'm going to manipulate this so that I know what cosine of angle C will equal. So that would be 5 squared minus 7 squared minus 8 squared all over the coefficient product, negative 2 times 8 times 7. Okay. Then, of course, we'll take the inverse of that. Okay, so let's get rid of this. Okay, so cosine inverse of 5 squared minus 7 squared minus 8 squared all over negative 2 times, oops, times 7 times 8. All right. So what should I get as an angle measure when I do this? Okay, so I'm getting 38.2. All right, so I don't have to stand up again. Let me go ahead and do this. I am getting better with the mouse. I've been practicing with that, if you can't tell. Thank you, Eli. I appreciate that. Okay, so now I'm going to use that measure with the formula to go ahead and figure out what it is. So the area is going to equal, now since we're going with angle C, I'm going to take half of what? Okay, 8 times 7 times the sine, oops, wrote out a weird sign there, of the 38.2 that we just found. Okay. And whatever unit of measurement it is here, if it's feet, it'd be square feet, square meters, I mean, whatever that turns out to be. But I'm going to go ahead and use the approximate value in the calculator. And I'm going to do one more thing. I'm going to go ahead and just put 0.5 times 8 times 7. And, you know, you can go ahead and easily take care of that, half of 56. But sine of this one, bless you. So how many square units am I looking at? There we go, 17.3 square units. Good, 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 good. Okay, any questions so far on law of cosines? Anybody having a hard time? Not seeing where anything's coming from. Okay. Oh, it's already 2:02. Okay, well, I guess I'll basically just go ahead and introduce this, and then we can go ahead and wrap this up tomorrow. That'll work out. I should, if that's the case, be able to give you a little time tomorrow to work on your assignment. We'll have the quiz Thursday. Hopefully start perimeter area, all the geometry review by Friday. So let me go ahead and at least show you what these are right here. We have what's called a true bearing and a compass bearing. And this is another idea that IB does differently. I've never heard it referred to as a compass bearing. I've always heard it referred to as a quadrant bearing, because that particular measure is always going to be restricted to one quadrant of your grid. But a true bearing, it measures the direction of travel by comparing it with true north direction. The measurements are always taken in the clockwise direction from north. Okay, so we have an example right here that's already done for us. Draw the bearing of 72 degrees T. Now again, this is another difference. If you're not told that it's true bearing, typically true bearing measurements are always going to be given in 3 digits. So the way I was always instructed, if I wanted to show that this was 72 degrees from true north, then I would say 0, 72 degrees. because it's always got to be that. But the way that IB is going to use the notation, if you put that capital T at the end, well, that means we're talking about true bearing. Okay, so if I were to look at this guy right here, okay, get a little cross section. So here's north, south, east, and west. True bearing always starts at true north and just rotates all the way around clockwise until I get back all the way around. And how many degrees are in a full revolution? 360. So you won't be going past 360. Okay, so does that make sense? So if I were to, well, I'll wait till tomorrow to show you another example, but you'll notice here, the 72 degrees, we just rotated 72 degrees, so you're still in the first quadrant. Okay. Now, compared to that, quadrant bearing, the direction is often quoted as an angle east or west of north or south. Bless you. Directions quoted in this manner are known as compass bearings. So these are always going to start with either north or south. That tells you what part of the y-axis to look at. North, you go to the positive y-axis, south to the negative y-axis, and then from there, you rotate left or right. Okay, so you go north or south, and then you go east or west based on that. So in this case here, north 48 degrees east. Okay, let's see, I started up at the positive, I rotated right because it says east. So what if I were to give you something like, oh, let's say south 30 degrees west. What quadrant would that be in? 1, 2, 3, or 4? Yeah, that'd be in 3. So because of the south, I'd have to start here, and then I know I'd have to rotate left because it says west. So maybe this right here. Okay. You always rotate left or right off of the y-axis with a quadrant bearing. Okay. So that's the difference between the two. So in this case right here, while this measure would be south 30 degrees west, if I wanted to go ahead and write that as a true bearing, then I'd have to start here and rotate all the way around. So what's 180 plus 30? 210. So that would be 210 as a true bearing. But you see how they're the same measurement? So it just depends on what you're using. Emily, did you have a question? Oh, that's your question? Okay. And we're going to take a look at that, and I think we had maybe a few more word problems, and then we might be done. Yep, okay. So we should be able to finish up this packet tomorrow. Any questions? All right. Well, let me go ahead and shut this.